All right, guys, in class on Wednesday, I had presented this nice adjoint theorem, which allows you to find the inverse of a matrix without having to do elementary row operations. In other words, without having to do the Gauss-Jordan method. So essentially, to find the inverse of a matrix, what you can do is find what's called the adjoint of A, and then just divide by the determinant. And because A is invertible, in order for this to be possible, you're not dividing by 0 here. Okay? So I didn't have a chance to justify the formula, and I hate just giving a formula out without a justification. So I'm just going to very quickly go through it, just so you can see it. All right? It's a little bit theoretical, but it's not too bad. So just remember real quick with me that the adjoint of A is just the transpose of the matrix of cofactors. So you build this matrix where you replace each entry of capital A with its corresponding cofactor. So, basically, the matrix of cofactors, the entries of that are just the cofactors Cij. And then, of course, when you transpose that, remember that the transpose just interchanges rows and columns. So the ith row jth column will become the jth row ith column. They just switch positions. And so the entries of the adjoint matrix, if I want to know the ij entry of the adjoint matrix, it's really just the ji cofactor. Okay? Question is, why does it give us this as a formula for A inverse? So I'm going to show that to you really quickly. Okay? We need one little observation before I can really give you it'll be a very, very quick proof once I show you one little observation. Let's suppose that the matrix A looks like this. Okay, so it looks something like this. Just these are the entries: A11, A12, A13, etc., 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 all the way down the line. Okay, I want to imagine that I do an operation here where I take the ith row and I add it to the jth row. So this is an elementary row operation. What's going to happen if I do that is I'm going to get a new matrix, which I'm going to call B. And all of the rows of the original matrix are going to stay the same, of course, except for the jth row. And in the jth row, you will have added the ith row to it. So you'll have AI1 plus AJ1, and then AI2 plus AJ2, etc., etc., etc. Okay, so that's how that's going to look. And if you imagine now finding the determinant of this matrix, right? Imagine that you cofactor expand along the jth row. So this right here is the jth row of this matrix B. Okay? So you're just going to do cofactor expansion. It's pretty much the same as the matrix A, except for this one row, the jth row, where we added row I to it. Okay, so what do we get when we cofactor expand that thing? Well, you're going to get, so the determinant here, you're going to get, AI1 plus AJ1 times CJ1, right? Because this is, that's the first entry, right? We're doing the whole expansion. So if I go across this row, I take the entries of this row times the cofactors from this row. And the cofactors are attained by crossing off the rows and columns that go with those entries. Well, in other words, you're crossing off the jth row, and in this case, the first column. So it's the same as the J1 cofactor of the original matrix. So you just keep doing this all the way until you get to AIN plus AJN times CJN. Okay? And what is this going to be? This is going to give you the determinant of B. Okay? But it turns out that, look what ERO you did. You did the ERO that doesn't change the determinant at all. So this is the same as the determinant of A, right? And so if you now expand this thing, see, in other words, if you distribute these expressions, you're going to get things like AI1 CJ1 plus AJ1 CJ1. That's for this part, right? And then you're going to get a bunch of other terms. The last one is going to be AIN CJN plus AJN CJN. So you'll notice like the AJ1 CJ1 and so on up to AJN CJN, That's literally just the determinant of the matrix capital A, where you have expanded the jth row of it. Right? The terms that I've circled are just cofactor expansion along row J. So these circled parts add up to the determinant of A. And you've added to that the terms that I'm going to underline here in blue. These extra terms, therefore, see, the whole determinant has to be A. And in this expression, I have the determinant of A again, plus the blue terms that are underlined, I'm circling in blue right here. So what that means is that AI1 CJ1 plus AI2 CJ2, etc., where you have two different I's and J's going on here. That's the sum of the blue terms, right? That actually has to cancel out to 0 because the non-blue terms add up to the determinant of A, which is what's on the left-hand side. So all I'm trying to say here is that when you take the entries from the ith row and multiply them by the cofactors from the jth row, you get 0. Okay? You get absolutely 0. So we need that little fact to explain this adjoint theorem. So now that I've got that, I'm going to come back and give you a very, very quick proof, quick justification. I'm going to keep this box here circled, but I'm going to give you a very quick justification. See, you can always rewind the video and go back and see what I had written there if you need to. But I'm just going to justify this adjoint theorem really quickly. Okay, so I'm going to do that by setting B equal to 1 over, I'm just going to give this a new name, 1 over the determinant of A times the adjoint of A. I'm going to call that B. Okay? And I claim that the inverse of A is B. So now here's a very important thing to remember. If I want to verify that two matrices are inverses of each other, what I should do to check that is multiply them together and see if I get the identity matrix. Okay? So that's what I'm going to do right now. I'm going to take A times B, and I'm hopefully going to get the identity matrix. So let me just show you that is the case. What I'm going to do to show it to you is I'm going to look at what the ij entry of A times B is. If I is equal to j, then I'm talking about the main diagonal, and hopefully the answer will be that the entry is equal to 1. If I does not equal j, then hopefully the answer is going to be 0, right? So how do I find the ij entry of this product? Well, as you remember, we have this dot product process for multiplying matrices together. So I'm going to take the dot product of the ith row of A with the jth column of B. So I'm going to get AI1 B1j plus AI2 B2j plus dot 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 plus AIN BNJ. It's going to look just like that. Okay? Now, what are these BI, so the A1I, or sorry, the AI1, this is AI1 right here, is fine. B1J, what is that? Well, first of all, there's a determinant of A on the bottom of every single entry of B. And the 1J entry of the adjoint matrix, okay, the 1J entry is actually CJ1, right? CJ1, just like that. All right, and then I'm going to do that again with the next term. AI2, the B2J entry is coming from this expression for B. The determinant of A is on the bottom, and on top, the B2J entry comes from the adjoint. If I put in 2 for I, I'm going to get CJ2. And we keep going like that. AIN times CJN over the determinant of A. Okay. You can kind of already see what's going to happen, right? First of all, you have the determinant of A on the bottom of everything. And on top, you have A1I CJ1 plus I'm sorry, I said that wrong. I meant AI1 CJ1, AI2 CJ2, and so on up to AINCJN, which is actually exactly this right here, this formula right here. If I does not equal j, remember that if I multiply the entries from the ith row by the cofactors from the jth row, it adds up to 0. So what that means is that this fraction is 0 if I and j are two different rows. Remember, we were adding a multiple of one row to another, so the I and the j were not the same when I derived this equation down here. Okay? So we would get 0 in that case. On the other hand, if I does equal j, then what you have in the numerator is simply the cofactor expansion of the matrix, capital A, along that row. The ith row, jth row, doesn't matter. If I equals j, then you are simply cofactor expanding a row of the matrix, capital A. And so, of course, we know that what we get when we cofactor expand along a row is the determinant of the matrix. If we then divide by the determinant of the matrix, we're going to get a 1 here, right? So what that means then, is that the ij entry of A times B is either 0 or 1, and it's 1 on the main diagonal, and it's 0 everywhere else. So we conclude that A times B is the identity, which means that these two guys are inverses of each other. So the inverse of A is indeed this matrix B. And that's what this adjoint theorem says. Okay, I just wanted to show you the justification. This isn't, something I'm going to be testing you on necessarily per se, but I don't like to just give you formulas without a justification. So there you have it. You've got a little bit of the theory behind the equation now. Okay, great. Thanks so much.